Here's an example of finding the area of a region given in polar coordinates. Let's find the area enclosed by the curve r equals cosine 3 theta. So it's a very good idea in all of these problems to start by graphing the curve, because until you do that, you don't know what values of theta you might need, where this curve might intersect itself or another curve, what kinds of problems might arise, where the r might be positive or negative, and all kinds of things like that. So let's start by graphing our curve. So what does this curve look like? For r equals cosine of 3 theta. Well, if you've played around with the graphs of cosine of a number times theta or sine of a number times theta, you'll know that what you're going to get is some kind of a flower shape with a certain number of petals. And when the coefficient on theta is an odd number, you have a number of petals equal to the coefficient on theta. 3 petals in this case. And those petals are going to start on the positive x-axis because when our theta is equal to 0, then 3 theta is 0, and cosine of 0 is 1. So our r will be 1. So our petal has to start down here somewhere, go out, hit that point, and come back down. We're going to have 2 more petals. They'll go down like this, and around like this. And once you've completed those, as theta continues to increase, you'll just keep on going back around the curve in the same direction that you did before and keep tracing out the same curve over and over and over again. Now, I'd like to know a few things. First of all, what range of values, what interval does theta need to take on in order to trace out the entire curve once? So, over what interval should theta go to trace out the entire curve once? Well, it turns out that you can trace out one lobe, one leaf or petal of this shape here, by letting theta go from over here, negative pi over 6, up to pi over 6. That'll give you one petal of this curve. As theta progresses beyond pi over 6, more than pi over 6, you'll find that your r ends up being negative. And so as you are traveling around this part of the curve here, these values of theta, your r is actually negative, and you end up over in the 3rd quadrant because your r is negative. So over here, r is positive. And we're actually looking at values of theta. Over here, r is negative. And it turns out theta is between pi over 6 and pi over 2, the positive y-axis. But because r is negative, we end up in the 3rd quadrant instead of the 1st quadrant. Now, finally, this last lobe here, our r is positive. And it turns out that we can trace this out for theta between pi over 2 and 5 pi over 6. Now, it actually turns out if you let your theta start at here at 0 and go out to pi, you'll actually trace out this last chunk of the curve here, this part of the curve that lies in the 4th quadrant, with a negative value for r. You'll trace out that curve anyway, with theta going between 5 pi over 6 and pi. So, to trace out the entire curve, theta needs to go along an interval that has a width of pi. Now, that interval could go from negative pi over 6 to 5 pi over 6. Or it could go from 0 to pi. Or it could go from pi to 2 pi, for instance. So to trace out the entire curve, theta needs to go from negative pi over 6 to 5 pi over 6, or any interval with a width of pi. Such as the interval from 0 to pi, or the interval from pi to 2 pi. Any interval whose width is pi will allow theta to actually, will allow the curve to be traced out in its entirety. Now let's think about how to take advantage of this to help us find the area enclosed by the curve. What we care about is the area inside these three lobes. Now, you can take advantage of the symmetry of this curve here. The fact that those three lobes should actually all be the same curve. The fact that I didn't draw it exactly perfectly doesn't matter. The fact is they are all symmetrical, they are the same. So we don't actually need to find the area of the whole thing. We could just find the area of one of those lobes and multiply it by 3. So let's do that. To find the area enclosed by the curve, let's find the area of one lobe, and we'll multiply it by 3. Now, how do we find the area of one lobe? Well, let's just stick with that rightmost lobe, the one where theta goes between negative pi over 6 and pi over 6. So we're going to have an integral from negative pi over 6 up to pi over 6 of what? Well, the general formula for the area using polar coordinates is the integral of 1/2 r squared d theta. Now, if you take a look in the textbook, you can see a derivation of where this actually comes from. This comes from the fact that finding the area of a wedge of the circle, whose angle is d theta, is going to be exactly this. It's going to be 1/2 r squared d theta. So instead of making Riemann rectangles, whose area is y times dx, you're going to have sort of Riemann wedges of the circle whose area is 1/2 r squared d theta. Take a look at the textbook and see that derivation, or talk to me if you want more explanation on that. So let's just fill this in. We know what our r is, so we can fill the whole thing in here. This is going to be the integral from negative pi over 6 to pi over 6 of 1/2 r squared. Now our r is cosine of 3 theta. That's being squared, and then we have a d theta. So now our task is just to solve this integral. That's not too difficult. Let's make a little more space for ourselves. And let's try to solve this integral. So I'm looking at my integral now. I've got a constant term, a coefficient there, 1/2. I could pull that out in front of the integral if I choose to. I don't know if I'll bother. I think I'll just leave it. We've got cosine of 3 theta squared. Now, a coefficient on the theta is not too much of a problem. We know that when we are solving the integral, if we have a trig function of a coefficient of theta, we'll have to use a very simple u substitution where the u is 3 theta, and in the process we'll have to find ourselves dividing by the 3. So let's not bother to write that down and worry about that right now. We know that we can handle coefficients on the variable at a later point. What we don't know how to handle is the fact that we are squaring our cosine function. In fact, let me write this. what we have here is 1/2 cosine squared of 3 theta d theta. Now, we know that when our trig functions are being squared, or have an even power in general, it's going to be difficult to solve this by a u substitution. Now, again, the 3 theta, not really a problem here, but solving our integral, our antiderivative of cosine squared of anything, is difficult. What we need to use is the power-reducing formula, or the half-angle formula. Let's remind ourselves of what that is. The half-angle formula for cosine says that cosine squared of x, of anything really, is equal to 1/2 of 1 plus cosine of 2x. You could distribute that 1/2 if you chose to. I'm going to write it this way because it'll be easier to use for these purposes. Now, what this means is you can bring that power down by using this formula, replacing this expression with 1/2 of 1 plus cosine of 2x. Whatever the angle was, whatever was being plugged into the trig function originally, you're going to have to double that angle now when you rewrite it. So let's make use of that. This is equal to the integral of negative pi over 6 to pi over 6 of 1/2. Now I'm going to plug in, instead of cosine squared of 3 theta, I'll say 1/2, an extra 1/2 there, times 1 plus cosine of twice whatever the original angle was. My angle was 3 theta, so now I have to say 6 theta. The angle is now twice as big, times d theta. And now we're actually in pretty good shape here. This is not going to be too hard to solve. We can now actually compute the antiderivative. So 1/2 times 1/2 is 1/4. I'll just leave that alone here. And we're going to find the antiderivative of our expression here. So the antiderivative of 1 d theta is theta. It's not x because the variable here is theta. So it's theta. Okay. Plus the antiderivative of cosine of something is going to be sine of the same thing. But we technically needed to use a u substitution here, with the u being 6 theta. And to complete that u substitution, we'll have to divide by 6. So I'll put a 1/6 here. Okay, there we go. And we are going from negative pi over 6 up to pi over 6. So let's just work this out here. Plug in our bounds. We've got 1/4 of, right, theta is pi over 6 plus 1/6 sine of 6 pi over 6 minus 1/4 of negative pi over 6 plus 1/6 sine of negative 6 pi over 6. I'm plugging negative pi over 6 in for theta, but I've got a 6 theta there. Close that parenthesis. And we'll just work this out. So let's see. I've got a 1/4 times pi over 6. That's going to be pi over 24 plus 1/24. The sine of 6 pi over 6. Let's see. 6 pi over 6 is pi. The sine of pi is actually 0. So in fact, this whole thing goes to 0. I can get rid of that 1/24 that I wrote down. In fact, negative 6 pi over 6 is negative pi, and the sine of negative pi is also 0. So this other term here is also going to 0. So we're just going to have minus 1/4 times negative pi over 6. That's going to be plus pi over 24, which is equal to pi over 12. So we figured out the area of one of those 3 petals or lobes in the graph of r equals cosine 3 theta. The area of that is pi over 12. So to find the total area, like we said, we'll need to multiply the area of one lobe by 3, because all 3 lobes have the same area. So it's going to be 3 times pi over 12, which is pi over 4.